All right. Okay. Today's lecture is going to be on Turing machines. I assume you've all heard of Turing. Yeah? Anyone who's not heard of Turing? Just out of curiosity. It's not like you have to, right? Sorry? Oh, extra credit. It's all come down to points, right? Yeah. Yeah. Anyway, so the one part of the course is philosophical, I guess. Is what is the formal model of a computer, right? Is there one, and what is it, and what can we understand from knowing a model that is underlies all the computation we do? It tells us something about the limitations, something about the possibilities, and maybe gives us some guidance on maybe what can go beyond it, if there is one, right? So this question was the motivation for this question did not really come originally, at least from basically computing. People are always playing around with algorithms because they needed to compute things fast, right? But usually they are thinking about computing things fast from a numerical point of view, right? People have been calculating various quantities for a long time, right? They want to always do some additions, multiplications, and when the scientific revolution came, people were doing astronomical calculations. But even in the Greek times, they used to calculate things about areas and things like that, right? What is this? So when did this computation come, right? But let's see what we have seen so far, right? We saw that DFAs are a very simple model of computation, right? And then we didn't really cover it because of lack of time. The context-free languages, which are more richer than regular languages, they can be thought of as there's also a machine model called push-down automata, right? You can think of that as basically I have a DFA plus a stack, okay? And we didn't cover that, but you can think about right. So, I mean, the natural question maybe that we can at least ask in retrospect is that, is there the most general model of computer that can solve any computational problem, right? Well, we kind of, at least, for the current computers, we kind of did this counting argument, right? And said there couldn't be such a thing because we looked at the following issue. How many languages are there over 0, 1? What is the answer? Sorry? No, what did you say? Countable infinite. Yeah? Yeah? No, the number of languages is uncountable infinite, no? Okay, the number of languages is how many? It is a power set of sigma star. Okay? You shouldn't forget that. I'm going to say it again and again and again, right? But how many languages are there? Each language is a subset of strings, right? But the number of strings is countably infinite, right? So the number of subsets of, think of this as the number of strings as number of integers, right? And each language is a subset of integers, right? So the number of subsets, number of languages is the power set of an infinite set, right? Okay, so that's uncountable. Okay, okay. So that's very important to remember. Okay, but how many programs do we have? How many C programs or how many Java programs do we have? Countable infinite because they are just the number of strings, right? The number of programs is the same as the number of strings because each program is a string, right? So clearly the number of languages is way more than the number of programs we have, so there must be things which are not countable, right? Now you asked, I will put it on the exam, okay? Okay, but see, I've said it probably 4 times already. right? In the sense that the number of integers is countably infinite, right? And the number of subsets of integers is not countably infinite, right?
I think it's uncountably infinite Java program. Like you can have whatever program you want to do.
No, but each Java program is just what is it? It's a piece of code, no? It's a string. What do you give to your compiler? It's just a string, no? So how many Java programs are there? Can't be more than the number of strings over whatever alphabet you're using, which is finite.
I would think Java is more like a bunch of subsets of different strings.
No, how many Java programs are there? Right? Well, you know, each of the Java program is just a string, no? No? It's no more than the number of strings over whatever alphabet you pick. And let's pick ASCII or whatever, right? You know, ASCII is finite, right? And your Java program is just a string, finite string. Is a program allowed to be infinite? Your code allowed to be infinite? Your code is fixed length, right? I mean, and it cannot be an infinite string, it's a finite string. So how many finite strings are there? As many as the number of integers, no more than that. Okay, so that's, okay, all right? Okay, so clearly, you know, at least from a programming point of view, the number of programs is way less than the number of languages. So the question is, you know, clearly there are problems we cannot solve. Which ones are they, and how do we understand them, right? And that's the thing. But it's not enough to say that there are programs, there are problems that we cannot solve. There could be many different kinds of computers, right? It's not clear whether there's a universally general computer, right? And so people thought about this, and the motivation came from a mathematician, David Hilbert, because at the beginning of the 20th century, they ran into a lot of trouble with formalization of mathematics, right? Mathematics always used to be somewhat ad hoc, right? You know, even calculus and topology and various things were not very formal. People did calculations, things worked out, and then basically at the beginning of the 20th century, people became much more rigorous about what they wanted to prove, and say that the notion of the proof took on a more important aspect because they were running into problems with various paradoxes, and including Cantor's diagonalization argument and so on. So they were trying to figure out, maybe we could make it more systematic, right? So there was really a process there, and David Hilbert said, look, you know, we are in such a big mess. Let's try to make everything mechanical so that we don't make mistakes, right? As we know, dealing with infinity is always a little tricky. You know, what is really truth and so on, right? So he said, you know, can we make sure that we mechanize mathematics so that we don't make mistakes, right? And that was his thing, and so that, you know, we can run some computer and it knows very simple steps, and it will not make mistakes, right? And in particular, he said, okay, how can we mechanize mathematics? He said, okay, we start with some basic axioms, and then we say, you know, what do mathematicians and what do we do when we write a proof? We say, okay, now we'll start with some basic facts, and we use inference rules, right? Okay, you know, A implies B and B implies C, then we say A implies C. So the rules we use to deduce new facts are very finite, right? So we start with axioms, we have some inference rules, and then let's say that, you know, the only things that we can derive are using these axioms and this inference rule, right? So can we derive everything that we want to derive using this particular system of axioms and rules, and is everything that we derive the right thing, right? So that's we take it for granted that's truth, right? That, you know, that we assume that is always correct, right? That we derive only consistent truths, and that we can derive any truth that is out there, right? And it turns out that that was not so easy, right? And this, you might have heard of Gödel, right? He came along, he's a very famous logician, and at a very young age, right, 25, right? Not much older than you guys, right? He proved that, much to the consternation of all mathematicians, that any consistent logical system cannot prove all the true facts. Okay? That means there will be some theorems which are really true, but we cannot prove them. Okay, and that's very disturbing, right? You know, we would normally think that, you know, if something is true, we should be able to prove it. But the land of mathematics is not so simple. Okay, and it was a big surprise. It was not, you know, everybody was like, oh, mathematics is dead, right? Of course, it didn't die, right? But it really gave a new, you know, direction to what proof is. Okay, and it was a big. It took a while for people to settle down to saying, okay, we have to live with the reality that there are theorems that we cannot prove, right? And so this notion that, you know, this is all in the world of logic, but at the same time there was this impetus to say, okay, you know, look, you know, really, if you're going to mechanize mathematics, there must be something that we can automate, right? So what does it mean to automate, right? At that point, we did not have computers, right? This is all mathematicians talking to each other about at a very high level, not really being in a practical sense, but more at a philosophical level, okay? And then came Turing, a British mathematician, which, I mean, I don't know how many of you saw this movie about him called The Imitation Game. You know, it's sort of embellished, but it's kind of important. I mean, I saw it on the plane ride recently, right? You know, it's more about cryptanalysis than about his Turing machine. It's fun. I don't know how many of you know the history of Turing. Was the main person responsible for breaking the German codes, right? Enigma machine codes, and the way he did it is because he knew how to build a Turing machine. He built a machine to crack the Enigma code. Okay. And I mean, it's not so simple as that, but he's the father of many things, AI, cryptanalysis, and he's the one who defined formally, way before there was any notion of a computer, the notion of a computer and what it means to program, right? And in retrospect, you may say, you know, it is something trivial, but he was at 23, he did that, and this is his model of computation. Okay, so what did he define the computer as? He defined it as a very simple object, right? You have a DFA and you have a tape. Okay, so that's all he said is a computer, right? So let's understand this. Okay, we'll formalize this, right? So this is a DFA with infinite tape. What does the tape mean? The only difference is that the tape allows you to write on it. Okay. Remember, in a DFA, you had a tape, but there's only read-only tape, right? You could move the finite machine starts at the input is written on the tape, right? The machine starts at the left end of the tape, and what does it do? It walks along and changes state and comes to the end, and he has to decide whether to accept or not, right? Okay, I didn't do it in class, but you know, in the slides you might have seen something called a two-way DFA. You might say, okay, if it is a read-only tape, why don't you allow the machine to go back and forth on that tape? Yeah, that's a reasonable model, right? I have my input written on a tape. I have a finite control. Why should I only move left to right one step at a time and go all the way to the end? Maybe I want to go back and look at the symbol again, right? That's called a two-way DFA. Okay? In fact, the two-way DFA is not any more powerful than a one-way DFA. The proof is not obvious, but one can prove that. Okay? So the main limitation of a DFA is what? The tape is read-only, right? You can't write anything and store any extra information. Okay? What is a Turing machine? It's just a DFA, except that now I'm allowed to write on the tape. What does it mean? That I have storage now, right? I can do stuff. I mean, instead of storing things in my head, which is finite, I cannot store too much. I can say, oh look, I'll put down something so that I can remember it later on when I come. Okay? But this is still a DFA. All right? Okay? Okay, now we want to argue that this is really the most general computer. Okay? All right? So it is such a primitive machine. The reason why it is interesting is because it's so defined so simply so that there is no cheating. Okay? What does it mean there is no cheating? When we think of our program, right? When we say int I, we are kind of cheating, no? Why are we cheating? because that int is really only 32 bits, right? We pretend that it's an arbitrary large integer, right? But in reality, you cannot work with arbitrary large integers. So what does it mean to work with arbitrary large integers, right? If you can imagine a machine, how can a machine work with arbitrarily large integers? That doesn't make sense from a human point of view, right? And in one step, can I add billion digit numbers in constant time as the same as 2 digits? That's not real, right? I mean, in some sense, we are abstracting out. It is giving us this impression that, okay, because these are 32-bit integers or 64-bit integers, we will pretend that the addition takes constant time, right? But that's not mathematically sound, right? Because when you want to think about addition as a problem, you can't say, I only am interested in 32-bit integers, right? Okay, so this machine is so simple you cannot cheat like that, right? So, okay, what does it mean? So let's see. So these are the high-level goals. Because it's such a simple machine, convincing you fully that this is as general as your desktop is going to be not easy, right? So I have to hand wave, okay? I will hand wave at various times, right? I'll give you some idea, but you shouldn't think of these next 2 lectures as I'm going to give you any proofs which are really convincing, okay? Because it takes such a long time, even though some of them are very intuitive, okay? So what are the high-level goals of understanding this model? One is this Turing thesis that this is it. This is the most general computing device that you can imagine, okay? Okay, now you say, no, wait a second, who said that, right? Is there a proof? There is no proof, right? Because it's a thesis, that's why I call it a thesis. The reason why it's a thesis and not a proof is that no one has so far been able to come up with any other model of computation, any other computer, which cannot be simulated by a Turing machine, okay? So it's a thesis in so far in that no one has been able to come up with it. People have tried. They have tried, oh, maybe I can do some funky things with using physics and stuff. So far, all of them can be simulated using Turing machines, okay? Okay, so that's the thesis. We want to kind of get some idea of why that is the case. Now, it's very easy once you kind of understand the formal definition of Turing machine that every Turing machine can be represented as a string, just like every DFA can be represented as a string. You just write down the DFA, right? And so the number of Turing machines is no more than the number of strings, and we can get some insight into that. And perhaps one of the most interesting and important things which Turing himself did very early on is this notion of universal Turing machine, okay? So what does it mean, right? So when we think of our computer, what is interesting about our computer is that we use the same computer to run many programs, right? You might think that's obvious idea, okay? Now you take it for granted that, oh, from the beginning it must have been obvious that there is a single computer which can simulate all pieces of code, right? That was not obvious, okay? Historically, when they build computers specifically for each task, okay? The idea of stored program computing is usually attributed to von Neumann, who was the first one to actually try to build a real computer. And the idea goes back to Turing because he defined the notion of universal Turing machine, which we'll see. It's a very simple idea in retrospect, okay? But it's very important. Okay, because that underpins all our computing today. And what is all this? I mean, these high-level things. Once we kind of understand Turing machines, we'll forget about the Turing machine because it's a very low-level programming model. And then we'll say, okay, we can simulate it using C, and Turing machines are the same. So then we can stay at a very high level. Okay, but it's important to first understand this very low level. Okay. So what is really a Turing machine? Let's formalize it, right? It's a DFA plus tape. What does it mean? That we can write, we can read, and so on. So a Turing machine, like we did with DFAs and then with context free grammars and stuff, is given by basically a bunch of finite sets. One is a set of states for the DFA, right? Remember, it's a DFA plus, right, some other ability to write on the tape. So first, if it's a DFA, then we have to have a finite set of states, right? That's what the state of the DFA is, a finite set of states. And sigma is the alphabet, okay? Now sigma is the input alphabet, okay? Is the input alphabet, okay? It's like terminals or, okay? And gamma will come is what's called a tape alphabet, but we'll come to that. Delta is how does this DFA behave, right? We have to ask, what does this machine do? If it reads a symbol, it can change state, right? but we also have to understand that it can write things, so we have to define delta a little bit more elaborately. We'll come to that. And what is gamma? Gamma is going to be the tape alphabet. What is the tape alphabet? It means that we can write stuff on the tape which is not the same as the input alphabet. It should be at least as big as the input alphabet. It should include the input alphabet, but we are allowed to write on the tape extra symbols because we can do some storage. Okay? So this is called the tape alphabet, and sigma is a subset of the gamma. Okay? That is, we are allowing our tape alphabet to be bigger. We can add more symbols. And Q0 is the initial state. Okay? And this is important because how can we tell what's written on the tape from the rest of the tape? No? What is the meaning of that? There is a notion called there is a blank, right? If nothing is written on the tape, we think of it as having a blank. Okay? So we will assume that there is at least one symbol called blank, B for short, which is part of the tape alphabet, but is not part of the input alphabet. Okay? Input should not use blank. Okay? All right. This is not a hard concept, but it's okay. All right. So whatever is not written on the tape is blank. Okay? But we should somehow mathematically associate a symbol with it called B. Okay? And then there are two states: accept and reject. Okay? All right. So far so good. Okay. All right. So now let's think of the transition function. Right? What does the transition function do? So what does the DFA do when it reads the symbol? What does it do? It can go to a new state, right? So the transition function in DFA is, if I am in a particular state and I look at a symbol, what is the next state I go to, right? Okay, but in a Turing machine, if I am on a state and I'm looking at a symbol, what can I do? I go to the next state, but I'm allowed also to do what? I'm allowed to write something on it, right? Yeah? Okay, so I have to tell you, if I'm on a state and I'm reading a symbol from the tape, I can write something on the tape, right? Overwrite what is there, and I can either go right or left or stay put. Okay? The machine can do what? On reading a symbol in a state, it can go right, go left, stay put, and write something on the tape. Okay? Yeah? No, on the same symbol that you're reading. Okay? See, I forgot to tell you, that machine has a head, right? It's called, this picture is, okay? At any point, the Turing machine, his head is pointing to some position on the tape, right? So it is in a state and it is looking at a symbol on the tape, and what can it do? It can rewrite that symbol, go to the right, go to the left, or stay put. Okay? That's all the Turing machine can do, right? It's very local, it can't jump. Yeah. Yes, exactly. So that is what the transition function will tell you. The transition function is going to tell me for every state and for every symbol that is allowed on the tape, if I am in state Q and I see a symbol A in the tape, I should know precisely which state I go to, which symbol I'm going to rewrite on the tape, and whether I go to the left, right, or stay put. Okay? Oh, because the state is part of the DFA, that is a finite control. How do I know where my head is after I read? I don't have to move only left to right like a DFA. I can go this way, I can go that way, I can stay put. That's the power of the Turing machine. The head is allowed to stay where it is. The head is allowed to move right or allowed to move left on the tape. So, but Q is just telling me what the state of this control is. So remember, the machine, it looks like this, right? It has a bunch of states. Which state it is in? But where is the head after I read this symbol? Right? How do I know where is the head? Should I go right or go right? Okay? Is that all right? Yeah? Yeah. Yeah, I mean, think of it like that, if you don't want to write, you can just rewrite the same thing, okay? You can say, oh, why should I always rewrite? Maybe you can give you the option of not rewriting, but it's not going to change anything, okay? All right? Yeah? Any questions on the basic model? Yeah? It's a very simple machine, right? Yeah, very simple, right? Too simple in some ways, but there is a nice thing about too simplicity is that you can't cheat, right? Your head can only move one step at a time. You can only write one symbol and read one symbol at a time, right? So that's it. That's the machine model, right? Okay. Okay, so how do we represent it? Normally, remember, when we had a DFA, we said delta QA is just a state, right? But now you have to tell me three things. What are the three things you have to tell me? What is the new state you go to? What is the symbol you write on that where you are? And whether you move left or right, right? So what does this mean? That, if I'm in state Q and I'm reading symbol A on the tape, I will go to state P, I will rewrite A with B, and I'm going to move left. Yeah? Yeah. Yes. Okay. Yeah. Okay. And that's just, to simplify things. Okay. There is no big deal. Yeah. Okay. Yeah. No. It just means, this means that I'm allowed to tell you what to do, right? My transition function tells me what I should do. So this is an example, right? This is what this means is that this is saying that this machine, if it's in Q and it's reading A, will rewrite it with the B and will move left and go to state P. That's the meaning of this diagram. Okay? But the transition table has to tell me for every state Q and every symbol, what should it do? This is just an example. No, but I can change state, no? My machine is it has its own internal state, right? That's like a DFA, right? It has to change state, right? Okay, yeah. To think, okay. I mean, it is maybe a little confusing, but it's just DFA plus the ability to write and read on the tape and move, right? Okay. Okay. All right. Okay. So now to make sense of this, we have to say, properly understand it, to say, okay, what are the, when I think of a DFA, how can I describe the state of the DFA when it's reading some input? Right? I mean, I can say, oh, it is in this. It's very simple, right? Because it's on a particular state and how much of the input it has read, right? Okay, but in Turing machine, we have to know many things. We have to know what is the state of the machine, what is the state of what is the contents of the tape, and where is the head, right? Because the head is allowed to go left and right, right? It can go like this and go back, and it can do funky things, right? So to tell you where is the Turing machine, if I pause the button and say, and I look at the Turing machine, how can I tell you what is the contents of the thing? I have to tell you three things. I will tell you what is written on the tape, right? What are the contents of the tape? Where is the head? And what is the state of the machine, right? Yeah? Okay, so how do I say this, right? I say it compactly, right? I will tell you this using one string, right? How am I going to tell you? Look, I'm going to only tell you, I'll encode the contents of the current configuration, let's call it an ID or instantaneous description of a Turing machine's behavior by telling you that, I'll give you a string followed by the state followed by a string. What does it mean? This means the Turing machine tape contents are x1, x2, xi minus 1, xi plus 1, xn. The rest are blank. Okay? And the head is sitting here. And the machine is in state Q. Does it make sense? Yeah? If I want to describe it in one string, this is how I describe it. Okay? Okay. That's the instantaneous description. Okay. Now, so how do we say that, the Turing machine went from this content to that, this place to that place? If currently you're in this contents, what can the Turing machine do? Well, the head is here, and it is reading Q xi, and it did something where, its head moved one step to the left, it's in P now, and it rewrote xi with y, right? We can describe, how did the Turing machine evolve from one context to another context, right? Okay, so don't worry about this for now. Now we want to understand, what does it mean for this Turing, what does the Turing machine do, right? Okay, what does the Turing machine do? So where does it start? It starts on the leftmost symbol, right? Yeah, and the input is written on the tape, and the rest of the input is, after the input, what happens? It's all blanks, right? Okay. Now, in each step, it's going to do something based on its description, and at the end, what happens? Well, if it reaches the accept state at any point, we say that's it. It accepts the string. Okay. It reaches the reject state. We think of it as rejecting the string. Okay. Okay. Then it can do other things also, right? Okay. So how do we formalize this? We say that, if you start this machine with the input written on W and the head is on the leftmost position, if it ever reaches a configuration where you reach the accept state, you accept. Okay? Makes sense, right? If you jump to the accept state, that's it, you accept the string. Okay? If you jump to the reject state, you don't, that's a rejection, but you have to be a little bit careful. Okay. So important thing is that the Turing machine is not required to read all the input, right? It's not required to read all the input like a DFA. It can look at the first symbol and say, aha, accept, right? It's up to it, right? It's not required to read all the input, okay? And it can go back and forth as many times as it wants, right? There's no constraint on it, right? And it can do whatever it wants on the tape. It can completely erase the input. Right? It's not read only, it can just do funky things, right? Okay. Okay. So now what is the language accepted by this machine? We say, okay, any string, if you put it on the input and it started in the start state, if it goes to the accept state, then that string is accepted by that machine. Okay, that's the definition. Yeah? Okay, then there's a small subtlety with Turing machines is that when does it not accept a string? What does it mean it doesn't accept a string? Okay. Well, it can go to the reject state, right? Says, no, I don't want to accept this, right? Or it can fall off the left end of the tape, right? Suppose I'm on the leftmost end of the tape and my Turing machine asks me to move left. What does it mean? So now I didn't tell you what it means, right? It means the machine crashes. Okay? Okay? If it ever crashes from the leftmost end of the tape, that's it. It's dead, right? That means it's not accepting the string. Okay? And it could go into infinite loop. We didn't see this before, no? But we know it from programming. Yeah? The machine can go into an infinite loop, no? Yeah? Why? Think of a simple machine. Suppose it always moves to the right and does nothing else, right? Where will it go? It will keep on going, no? There is no limit to it, right? But there can be, that's not the only reason. I can define a simple machine which all it does is it will go one step right, one step left, one step right, one step left, right? It's not going to do anything, right? Other than just move back and forth for, right? So, see, already we see this machine has the ability to go into an infinite loop, right? It doesn't have to terminate, okay? So once you give it power not to terminate, then we have to understand what does it mean if I give you an input W, does it accept it or not? Aha, now we have four possibilities, right? On an input W, it can either go to an accept state, which means that we accept it, great. It can go into reject state, which is clear, reject. But it can go to infinite loop, or it can crash, right? So crashing is considered rejecting. Infinite loop is considered not accepting, okay? Okay. So, well, we know with the regular programs that it's very hard to know whether our program will go into an infinite loop, right? We write always buggy code, right, in many times. So it is a real problem that's coming up because we define the model in a rich enough fashion, okay? So, but what is the language accepted by the machine? It's all those strings such that if you start the machine on that string, it will go to an accept state. That is the language accepted by the machine, okay? That's very important. The only strings in that language are those strings such that the machine will go into an accept state. If a string is not in that language, what does it mean? Either the machine rejects it explicitly or goes in an infinite loop or crashes. All right? That's the definition. Okay. If that's the thing, if m doesn't accept, we may not be able to tell, right? Because it could be an infinite loop. Okay. Now, so this is a model of a machine, right? It's a computer, we say. Okay. What can it do? Right? We need to understand what it can do and why is it interesting. Okay. So, but before I do that, we will just we'll define two things. Let's go with this one first. We say that a language is decidable. Okay. If there is a Turing machine such that the following happens, which is what we think of as a real algorithms, right? For every input, the Turing machine will halt and either say accept or reject. Okay? It never goes into infinite loop, it never crashes. Okay? Right? A language is decidable if there's a Turing machine such that on every input, the machine will stop and either say accept or reject. Okay? And the language is precisely all those strings that the Turing machine accepts. Okay? Okay, now we are going to define something weaker. A language is called recursively enumerable if the following weaker condition is true. A language is recursively enumerable if there is a Turing machine such that for every string in the language, the Turing machine will stop and say accept. Okay? But for strings which are not in the language, the Turing machine either will say reject or crash or may not halt. Okay? Okay? So this is the definition. You don't worry about the subtlety of this, but this is the thing that we care about, right? What do we want our algorithms to do? We don't want them to go in infinite loop, right? We don't want to. I mean, we want algorithms which will actually, for every input, they'll either say yes or no, right? We don't want them to go into infinite loop or crash, right? This is what we are interested in, right? But because of the complexity of reasoning with these machines, we will think a little bit about this class as well, okay? We will come back to it, don't worry, okay? Okay. So,
What do you mean by crashing?
Crashing means it falls off the left end of the tape, right? Okay, we'll define it because that's the main thing, okay? But we'll talk about other things also. So now the question is, are there what are the things that we want to compute? Are they recursive? Are they decidable? Are they recursively enumerable? What's the difference? And so we'll come to this, right? But let's get our hands dirty and design a Turing machine. It's painful, but we'll do some simple things, okay? Okay, because it's so simple, right? It's like programming not even in assembly language. It's programming in Turing machines, right? It's very, very painful because it's so simple. To do anything interesting, you just have to, right? It's not. It is very painful, right? So what is this? I am designing a Turing machine which will accept this string 0 to the n, 1 to the n. Okay. So what should think of a machine which should only accept these strings, right? How will you design a Turing machine which accepts these strings? Let me remove that, right? How will you design a Turing machine? At a high level, what would you want to do? So I write a string on the tape, right? And you should accept it only if it is equal number of zeros followed by equal number of ones. What will you do? High level, how will you write a program for it? Don't worry about the precise details, yeah? Yeah, so you said keep count of. Okay, how will you count? This is already hard, I claim. Why? Why is it already hard to count? Okay, so let's even forget about that, right? Let's say, I give you a string of zeros and you want to compute the number of zeros in binary. Okay? Okay, so what do I want to do? I give you a string, doesn't have to be zeros. I just give you some string, right? And you have to design a Turing machine that will, at the end of that, write a hash and then give you the length of the string in binary. How will you do it? No, but I'm saying that I'm trying to tell you why it is hard. Because you don't have, we are used to programming where you have a count, integer, right? You say +1, right? But you don't have that in the Turing machine. You have to put it into the DFA, okay? There's no cheating allowed in Turing machine. You see? You can't say, I'm going to count the number of zeros and I'll write it down. Okay, but you'd have to tell me how with a finite state machine you can actually even count. Okay, it's painful, right? Okay, the nice thing, yeah. No, okay, so this is what I'm trying to tell you. You cannot count and keep it in the finite states memory because the machine, the DFA cannot remember. Yeah? Yeah, right, that's a better method, right? High level, what we do is we are not going to count because that is too complicated already, okay? Because nobody is going to give you an int where you can +1 because there is no int, remember? Right, we are very simple. Our DFA cannot remember anything, right? If you want to count, you have to write it on the tape and remember, okay? Because its number of states is small, right? Fixed, okay? And my string can be long. So here is the strategy, right? What this does, we'll do some simulation, is that it does something even very simple. Because I'm going to count 0 to the n, 1 to the n, you'll start reading, and if it is a 0, what will it do? It'll put a tick on that, okay? Or as you said, I'll convert that 0 into 0 prime, because that's my tape alphabet, right? And then I walk till I hit a 1, and I'll convert that and say, I saw a 0, I better see a 1, right? Okay? And I'll put a tick on 1, and I come back, and see if there are any more zeros, and I keep walking back and forth, okay, marking things, not counting things, but marking things, okay, because it's much easier to mark than to count, because our model is so simple, right? Okay, so let me illustrate this machine, right? What does it do? It starts with this, right? Let's say, okay, let's see what it does if I give you 0, 1, okay? Okay, so let's see. Suppose my input on the tape is 0, 1, and then blanks, right? What does this do? What does this machine do? So it starts at this state, right? If it sees a 0, what does this mean? It will make it into 0 prime, right? It's my tape symbol, right? I didn't specify exactly. So what does it do? It makes it 0 prime. What is the meaning of this? It means that I have seen a 0, now I need to better see a 1, right? Okay. So it starts walking to the right and say, I have to find a 1 now, okay? And it goes here, and what should you do? It will skip all zeros, right? If there could be many zeros after the initial 0, it skips all zeros till it hits a 1, okay? Okay, so, and then, if it sees a 1, it will convert into 1 prime, okay? So in this case, what does it do? After it saw a 0, the head was here, now the head is here, and its state was this one, and now it'll convert, it'll convert this, so this was here, and then after this, it will make it 0 prime, 1 prime, and the head will be here, okay? Right? And then, because now what does it do? I don't know if I made a mistake here. If it sees a 1, it should move. Yeah, okay. No, so it went to this state, right? And if it sees 1 prime, okay, if it sees 0, it will go this. If it sees a 0 prime, yeah. So, okay. So it is in, okay, so it started in this state, yeah? What did it do? It converted the 0 into a 0 prime, right? Moved right, looking for a 1, right? So it went to this state and its head was here, right? Actually that's, okay. So it started, okay, let me, okay, all right. Okay, so it went from here, replaced it with 0 prime and went here, right? And it stayed here. This state is find and mark 1, and then it found a 1, and so it replaced it with 1 prime and moved left, right? That's what its meaning is, right? And now it is looking for a next 0, right? Well, it didn't find, what is it looking here? It's looking for a 0 prime, so it went to this state and moved right. So and then it'll move right. It doesn't do anything, replaces it, and it is now in this state. And from here, it'll go to this state, and it'll see a blank and it'll accept. Okay. So let's do a slightly more general example so that you see what it does. Right. Suppose it has so it has 0, 0, 0, 1, 1, 1. Okay, what is it really doing, right? It starts with this 0. It says, I'm going to convert to 0 prime. Okay, and then it has to go look for a 1, and then it'll come here. It'll convert it into 1 prime. It'll go back and looking for another 0. Mark it as 0 prime. Go back looking for another 1. Okay. Now there are some transitions which are not shown. Okay. If there is no transition, it means that it will crash. Okay? The convention is, because we don't want to draw so many things, that if you don't see a transition and the tape symbol is not what is there, it is going to crash. Okay? Alternatively, you can put arrows to the reject state. Okay? To avoid cluttering up this thing, we will use the convention that if you are seeing you are in a state and there is no transition on a symbol, you crash. Right? Okay. Now you have to, it is very painful to make sure that this machine will not just accept anything which has equal number of zeros and ones. It better be all zeros before all ones, right? It's not easy to verify this. Okay. Okay. It is painful. I'm not going to convince you of that because it's really painful. Okay. Okay. So you say, okay, my God, what can this silly machine do? Right? Can it do anything interesting? If this is so hard for it, what can it do? And here I am claiming that this is the most general model of the computer, right? Okay, but that's the problem, is that this is so simply defined. It has its advantages, but the disadvantage is that it's not obvious it can do everything that we want it to do, okay? Because it looks so painful, okay? But so you can see some other examples. Let's see, can it do addition? Forget counting, let's do addition, right? Okay, how will you add two numbers? Okay, for simplicity, we are going to assume that our numbers are in binary and they are represented in this convenient form. That I have a dollar, because to make my leftmost symbol easy to understand, then a bunch of binary digits followed by hash, followed by the same number of binary digits. Okay, and I want to add these two numbers. Okay, is that clear? Same number, right? I want to add. How will you design a Turing machine to add these numbers? What can you do? So high level, right? We want to think out high level because the low level is really painful, right? But the important thing to remember that I want to stress is that your machine has only finite number of states. So you cannot remember, like a DFA, more than the finite number of information. So your control is this number of states. The state machine is just for control. If you want to remember anything very long, you have to put it on the tape. Okay? If you want to remember anything, you want to put it on the tape. So how will you do this addition? Yeah, you can have any number of states. But as long as the machine's state space is finite, and it should not depend on the input. That's all I'm trying to say. Right? You design the machine first, it should work for any arbitrary long input, just like your code, right? Okay. So how will you do this? Well, here is an idea, which you can see, right? So what you can do is that this machine will basically walk all the way to the right end of this string, okay? remember is it a 1 or a 0, and it also remembers the carry. It can remember one carry, it can store in its head, right? Because that's only one bit, right? In its state space, it can remember, right? The carry. It reads that, comes back to this. Once it finishes reading it, it'll erase it so that I'm done with it, and then comes back and adds it to this, right? And replaces it with not the 1 but 1 hat to indicate that I've already added it and it is no longer the right thing for me to add. So what it is doing is that it is going to add the last digit of this with the last digit of this, replace both of them so that it doesn't have to do it again, right? And go back, read the next digit, come back here, add to the next digit, but you'll remember the carry in its head, right? And keep on doing it, and eventually what we'll have is that the sum will be, this thing will be overwritten with the sum of the two numbers, okay? Okay, you imagine that you can do it, right? It is not hard to imagine that you can do it, right? But the only thing I want to point out is that you have to remember that the state of the machine is finite. It should work for all strings however long they are. That's the main thing you need to remember, okay? Just like your code, right? Okay? All right? So it's very painful, right? So painful that it seems like, but I claim that you can do everything. You can do addition, you can do multiplication, you can do subtraction. All the basic things that you want to do, you can do, but you have to do it very painfully. Okay? Because you can't do it in a, right? So, okay. So if you can do all this, well, how am I going to convince you that it's really as powerful as a general purpose computer? Well, we'll show you some tricks, right? And the tricks are not because you are going to design or write programs in this programming language. It is to show you that really, some attempt to show you that even though it looks simple, you can do all the things that you expect your computer to do. And in fact, because the model is so simple and no cheating is allowed, you will see, in fact, even for you'll have even a better understanding of some of the issues in computer architecture. Okay, how exactly do you implement things like subroutines? Okay, what I mean, how is your computer implementing things like subroutines, right? And recursion, right? Things like that, are possible to do it with this, right? So here is some extensions of the basic model that people will naturally think of. Why did you design it? Why did you choose to have the tape going in one direction? Why didn't you let the tape go in the other direction, right? Why did Turing decide? Well, let's see. So before I do that, remember we already saw some tricks, like checking of symbols is a nice trick, right? Because it's a simple technique. You don't have to count and all that. You can remember by keeping track of that. We already saw that. One thing, which is annoying was that what is the silly thing of falling off the left hand of the tape, right? Come on, I mean, that seems like a silly thing, no? I mean, we should define the machine not to fall off the left hand of the tape, right? Okay, but I claim that it's not really, it's not fundamental. So why is it not fundamental? I claim it's easy to do the following, right? If I give you a string on the tape, I can move it one step over. I can shift it to any small number of symbols, right? How can you do that? So can you write a Turing machine which does the only following thing? It looks at the tape and just moves all the tape symbols, not the blanks, but the input one step over. What should it do? Okay, it just needs to say copy everything from here to one. What should you do? Yeah. Yeah, so he's saying, go all the way to the end of the tape, copy that thing one symbol, right? Can you do it even better? Right? This is just for fun, right? I only want to scan once. I don't want to go, I write so many times, right? Okay, this is just for getting a feel, right? Okay, remember, you can do the following, right? You're staying in first step. You remember the symbol on that in the finite state, go to the next thing, overwrite that, remember that in your finite state, overwrite that. You can do one scan from left to right by remembering what you saw in the previous step and overwriting it in the next guy. So this will be just one scan from left to right. Yeah? Just a trick, right? Why only one shift? I can do two shifts like that too, right? If I want to shift it by 10 symbols, I can remember in the finite state the 10 symbols I've seen in the past, yeah? And then overwrite, right? That's what this is saying, okay? You can shift. So once you shift, what can you assume? You can assume that there is a dollar in front of your input and the dollar will tell you that this is the leftmost part of the tape, right? You can shift the symbols, put a dollar there, and you will never crash from the left-hand side. Yeah, because I now receive a dollar, I said, oh, yeah, I shouldn't move left because I know where the end of the tape is, right? You can convert any Turing machine into a new Turing machine which will never crash on the left end of the tape, right? Yeah, that makes sense? Yeah, so just to see what you can do. Okay, and just like remember DFA, what did we do? DFAs can, in the finite state, store multiple pieces of information, right? So you can use that same trick here too. So all the DFA tricks you can use. Okay, subroutines are very important. We'll come to it. It's tricky. But let's see this. What if I had an infinite tape this way and that way, right? Why did I choose the tape to go only infinite in one way? I claim it is not a big deal. You can define the tape to be going this way and that way also. Why? Okay, what does it mean, why? It means what I want to show you is that any Turing machine which has infinite tape on left and right, if you can do something interesting on it, you can do it also on a machine which has tape going only infinite in one direction. Okay? So what this is called is a simulation argument. What is a simulation argument? I'm going to try to convince you that whatever the Turing machine can do with the tape going both directions, I can simulate it with a Turing machine, another Turing machine, which has tape only going in one direction. Okay, how will you do that? How can you simulate this tape with one tape going only in the thing? I will fold the tape, right? Okay, what does it mean, fold the tape? If you think of the tape is has indexed as 0, 1, 2, 3 going this way, minus 1 going this way, I'm going to put 0 here, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, 5, minus 5 like this, right? Okay, I'll pretend that this is my tape. What does it mean? That I'm mapping this negative side of the tape to the only one, because I only have a number line on this side, right? Right? I'm going to intersperse these guys with the negative numbers, right? So I took the tape, I have an origin, I am folding the infinite tape on itself, right? Okay? And so I have to create room for it, so I create two symbols instead of one symbol, right? I mean one. So this is, okay? Now I claim that a Turing machine which operates on this, I can simulate on this. Okay? Okay, how will I do that? Okay. So I can, in my DFA, I can remember whether I was in the negative portion of the tape or on the positive portion of the tape. Yeah. Okay. Because that's just one bit, no? Am I in the negative portion of the tape or on the positive portion of the tape? Okay. So that will tell me when I'm reading here, you know, I'm really on the -1, right? If I have to go left on -1, what does it mean? Where should I go? If the original machine was going to go left from -1, where would it go? To -2, right? Okay, but -2 is not here. -2 is where? Here, right? So I can say, aha, if the old machine was going to go left from a negative position, I have to go 2 steps right on this new machine. Okay? If the old machine was on a positive part of the tape and it's going to move right, 1 step, I have to move 2 steps on this new tape. Right? 2 steps is not any different from 1 step, no? I can allow my Turing machine to move maybe 3 steps at a time, 1 step at a time, right? Because I can simulate that, right? Yeah? Okay? So that's it. That's how you fold the negative tape into the one-sided tape. Okay? So what I'm trying to convince you is that the basic model is not as weak as you think it is, right? And that it can do things. These are tricks that we all use in programming, but these were thought about very early on, right? Okay, so another programming trick, right? Why did I have only one tape, right? You know, maybe you say I want 10 tapes. It's nice for me to have 10 tapes, no? Instead of having one tape, I can store more information, right? Okay, does it make sense, right? I have 10 tapes, yeah? Why not, right? You know, who told me that one is interesting? I can create 2 tapes, right? So yeah, sure, you can have 10 tapes. Let's talk about 4. It's called, instead of think of 10 tapes because we'll see something else, we'll think of it as, oh look, I have you know, multiple tracks, right? So I can store, you know, different symbols on each track, right? And what is my basic move of the Turing machine? It can do the following. Its head is in at any one point. Head is here. It can simultaneously read all these symbols, okay, and decide to move right or left. And it can do the following more interesting thing. It can read all of this and say, I only want to change one of these things and then move right. Okay, I don't have to change all of this, right? I can say on track 3, I want to change something, right? So how will my transitions look like? It look like this. On a state queue, if I'm reading this, if I read a 0 in the second track, I will move to P, I will overwrite the 4th guy to 1 and move right, right? That's the thing. But I claim that I can simulate this by a bigger alphabet, right? I mean, what is this, right? These are 4 symbols written on it. I can think of my new alphabet as a much bigger alphabet which encodes 4 of them together in one symbol, right? It's not really any different, no? Yeah, that makes sense? Yeah, oh sure, what is the big deal? I can think of my symbol as like this 4 tuple, right? Okay, it's just that, you know, it helps me program more easily, right? If I have more tracks, it'll help me more, okay? Okay, so it's not any different, right? You're somewhat convinced that it's not any different. Okay, a more interesting thing is I have multiple tapes, but I also have multiple heads, okay? Okay, this is more interesting. This is more powerful. Okay, this is trickier. Okay, okay. So okay, let me show you. Like okay, this is Lenny's old cartoon slides. I like. Okay, so what does it mean, right? Okay, so I instead of doing the formal thing, let's look at pictures. Okay. So here I have a Turing machine and I want to decide the following language. W hash W. That is, I need to accept all strings which are 2 strings which are the same separated by a hash. Yeah? How will you do it? You need an algorithm to decide if it should only accept strings of the form W hash W. How will you do it? So, see, that is, I give you something, hash something, and you want to check that these 2 strings are the same. How will you design a Turing machine? Very simple, no? Yeah. What will you do? Yeah. Yeah, so it's simple, right? You start here and say, this is the 1. I'll go all the way till I see a hash. I'll make sure that there's a 1 there, right? Mark it off and go back and forth, back and forth, back and forth, right? Yeah? Seems, yeah, right, okay. Okay, if the length of the string is n, how many steps are we doing in this way? Well, for each symbol we have to walk about length n, no? Yeah. So total we spend about n square time, right? If you think of time as 1 step, right? Because for every ticking off, I need to spend n time to walk all the way, right? Yeah? Okay, but suppose I had 2 tapes. What is it? Not, I have 2 tapes, right? I have 2 heads now, and the heads can move independently. They're not tied like this, right? So I have 2 tapes. I'm allowed to do the following. I have 1 head here, 1 head here, and what's my transition function? Depending on what these 2 heads are looking at, I can do the following. I can rewrite those symbols separately, and this guy can move left, I can move right, or that guy can stay put, I can move left, right? So that's is the model kind of clear? So I'm seeing 2 symbols, my 2 heads, but the heads can move independently. I can decide to keep 1 head this way, or move that head, or move this head, or move that head, right? Okay. Yeah, is the model kind of clear? that I'm allowed to move the heads, and so one head could be very far away and one head could be here, right, all the way to the left. So if I give you that power, I can make this much faster. Why? If I had 2 tapes and 2 heads, what can I do? Okay, I claim I can do the following, right? I can go first and maybe copy this string, okay, come back, right? So I copy this string into the second tape, right? I'll make one head go on this and one head go on this and read off whether they are the same, no? Yeah? The 2 heads will allow me to do that, right? Okay, what happens because of that? My running time will become roughly n instead of n square, no? That make sense? Or no? If I had 2 heads, I can copy one and then I don't have to go back and forth, no? Okay, so roughly, yeah? Okay, so clearly 2 heads is making our life better, no? Yeah? So why shouldn't we use 2 heads? Because that seems like a reasonable model of computation. I can create 2 heads and all, right? Now the question is, is it really fundamental or is it just efficiency, right? Or really, right? So the question is, can we simulate this 2-headed machine with 1 head regular machine? How? Yeah? Oh yes, that's tricky. That's tricky. You can't use product construction because the tape is it can be arbitrarily long. Remember, it's a good idea, but what do we need to remember now? The heads could be very far apart, no? Yeah? The one head could be, gazillion steps all the way to the right, one head could be all the way in the... So it's not enough to know the states. The state is the same, but the location of the heads can be very, very, very far apart, and we cannot remember where the location of the heads are because we have a finite number of states. Okay, so how can we do it? Yeah? Every other one is the tape. Yeah, but the important thing is, how do you remember where the heads are? Okay, that's the key thing, right? You have to remember where the heads are. Yeah. The head is, yeah. Yes, that's a good idea. So what we will do is that we will use a tick mark to remember where the heads were. Okay? Okay? We will use a tape. Remember, we cannot store the location of the head in our finite states because that's a finite states, right? The head could be very far away. So what we will do instead is that we will simulate this 2 heads machine with 4 tracks, right? In this following fashion. The first track will store the contents of the first tape. The second track is just empty except for 1 tick to know where the head is. And the third track will be where the contents of the second tape are. And the fourth track, there's again the same thing, we'll remember where the head is. Okay? Alright? Okay? We are using the tape to remember where the head is. So now we have to be a little careful. What is the machine going to do? The machine is always going to be at the left end of the tape. Okay? The first thing, so it is trying to simulate this complicated 2-headed machine, right? But it knows where the heads are. So what it will do first is, it will keep walking to the right, okay? To do what? To figure out where the heads of the old machine are. Okay? Why does it need to know that? Because it needs to know what are the 2 heads actually reading on their tapes, right? Remember, we are designing a new Turing machine which has only one thing, and it has to simulate the behavior of this, right? So what does this machine do? this head is reading 1, this head is reading 1, and based on these two symbols and the state of the machine, this machine will override these two symbols and move the heads independently, right? But how will my machine even know what where these two heads are? It's going to remember where this by putting a tick mark on the tracks, but it has to figure out, remember it can't count. So what it will do is that it will start at the left, it keeps walking, okay, till it sees a tick mark. When it sees a tick mark, what does it know? It knows that, one of the heads is here, right? Then it can read the symbol of that head in it, right? And it keeps walking till it sees all the tick marks, right? Once it sees all the tick marks, it knows all the symbols that the two heads were reading, right? That it can remember in its finite state. Then it knows which move to make, right? Yeah? It knows which move to make and also how to rewrite the symbols. But now it is all the way, it might be, it read this guy, but the head of the new machine is sitting here, right? So what does it need to do? It has to walk back all the way. Whenever it sees the tick marks of the old things, it makes the changes and goes all the way to the left end of the tape. Does it make sense? It cannot remember, so it keeps a tick mark where the heads of the old machine are, right? So it starts always to make one move of the old machine, this silly machine is going to start at the leftmost end of the tape always, right? It goes way all the way to the leftmost end of the tape. It says, okay, now I'm going to walk till I know where the heads of the old machine were. How does it remember the heads of the machine? By keeping a tick mark on its tracks. Okay? And each time it sees a tick mark on the right track, it memorizes the symbol that the old machine was seeing on its tape. It keeps walking till it sees all the tick marks on both the tapes, and then it knows what it should do, what the old machine would have done on its two things. Then it walks left now to implement that move, right? It goes back and says, now I know this head was here and I can remember what the old machine would have done. It would have replaced this 1 with a 0 and it moved this head. How is it going to move the head? By doing what? Putting a tick mark, right? If the head was supposed to move left, it will erase this tick mark and put a tick mark here. If the head was supposed to move right, it will erase this tick mark and put the tick mark there, right? And then it has to go and do it for all the positions of the old heads, and then it goes all the way back to the left end. So to implement one move of the two tape machine, this guy has to go all the way from the left end till the right end of the tape, all the way back, done. Okay? So it's very slow, right? Okay? So here is the thing, right? Does it make sense roughly? You have to go back and forth because that's how it remembers, right? So if one move of the old machine, how long does this guy take? It depends on the contents of how much the old machine wrote. Okay? So if the old machine took t times, this machine will take t square time. Okay? Because it has to write, it needs to go back and forth, because the length of the old machine in time t could have written a string of length t on its tape. And I have to spend t time steps back and forth, so that adds up to t squared. Okay? Okay? So hopefully you're getting the hang of the fact that this is a painful thing, but you can do it. Yeah.